we can start. Thank you to be here again. Today we presented Francesco. Francesco is a PhD student here in our department, of course. And today we'll speak about his PhD project and the caching approach for querying optimization on linked open data. Thank you so much.
Thank you, Laura. Thank you, everybody, for being here today. Today I'm going to present you our work on smart caching approach. And now we are working on optimizing the query processing for source selection in the web of data. And just a brief introduction. Today we're going to see some motivation and goals of our project. Then we are talking about a little on source selection for the linked data. And then we're going to see the caching approach we are developing now for the source selection. And then a first idea on relaxing the queries for optimizing also the source selection. And so we start with some motivation. And we can say that the web of the data, which is nowadays a fundamental part of the web, is a set of data that is published on the web by some various data providers in agree with some principles of the linked data. And we can define also, thanks to Delbru's definition in his paper, the web of data is an interlinked FDF dataset which is published on the web. And so, what are these principles of linked data? And so we can define linked data as a set of best practice to publish and connect and discover structured data on the web using some standard formats. Some rules are, for example, to use HTTP URIs to referentiate the real things in the world, and use the language Sparkle for expressing the requests, and also to provide useful information using these standards. And we can define that a RDF data source is identified by an URI and contains RDF data viewed as a set of triples. An example of this, we've got a source expressed by its URI, and so this is the example. Then these are the triples that the source contains. And so, for example, we have 5 triples expressed in a graph like this. And we can identify the subject, the predicate, and the object of this triple. Now we want to find all Mario's friends. Okay, so we know that we have a resource called Mario here, okay? And then we can express the query in Sparkle language. And so we have select the variable person, which is identified by the question mark and the name of the variable. And then we express, like SQL, that the person is a friend of Mario, okay? So what is done is to go inside the graph or in the triples. We look for the predicate friend of a friend and the object Mario, and then we select the subjects related to this predicate and object. And so we have here Fabio and Giulia. So the result is Fabio and Giulia, which are the bindings for this variable. So the motivation for our project is that since we are looking at this web of data, the query processing is enriched by new phases, like, for example, the source selection. This makes the query processing more costly, and also it might not guarantee the user satisfaction. So the idea is to exploit some additional information about the queries, such as user profiles, or the best one is the insights for previous request execution. So information, for example, like results of a query, or sources used for the query execution. And in this field, we have got some existing approach like materialized views and smart caching approach, which mainly uses the answers of the query, the past queries, as an input for improving the query processing. So they use these results and then they try to speed up the query processing using these results for obviously similar queries, okay? And so we want to investigate how this information about similar queries that are recurring in the time, obviously, can be exploited to efficiently and effectively help the query processing on complex requests. But obviously, we are talking about data spaces and so data sources that are diverse and dynamic, so contain sources that are heterogeneous and poorly controlled. The idea is so to take advantage of this prior processing in order to obtain shortcuts in different points of the query processing stack. We know that to retrieve data from a data set given a query, we have to go through various steps inside the query processing. So we think that using information not only at the last level, so the response of a query, but also at different level of the stack, can help the query processing to be more efficient and more effective. Our approach is a generalization of smart caching methods that are proposed. But obviously, we don't want to associate with past queries only the result, but we want to associate also other kind of information. In this presentation, I am focusing only on the source selection. So the information associated with the queries are the sources used for past evaluations. Here we have just a picture that describes the query processing stack. We have, for example, a phase of source selection, a phase of query optimization, a phase of query execution, and we see that most of the existing approach have a shortcut only here, right before the result. And we want to create some general framework that allows us to get information at this point or at this point, and so on. Just to be more clear, we have an example that underlines the dynamicity of the data at the source point of view, but also from the point of view of the query. And so, for example, we want to see that a user might ask for the authors of a figurative artworks that he is watching in that moment, so located close to his position. And also he wants information about other places where such authors are currently exposing. So we have a dynamicity on the position of the user that might shift his position in one moment and another, but also about the places where these authors are exposing. Because we might think about the Palazzo Ducale, now there is an exhibition, but we may think that in 1 month it may change, okay? So this query can be represented as a graph like that. So we have some variables expressed like in the Sparkle language. But obviously we can translate this graph inside a Sparkle query, which is represented like this. So we haven't defined yet the source selection. So what is source selection? Source selection is a determination of a set of data sources that we want to look up to retrieve data from a query that the user poses, okay? So we have a linked data query expressed in Sparkle language, and we want to determine the set of sources that gives us a result. A data source obviously is relevant for a query if it contains the data that contributes to the query result. For this reason, various strategies have been proposed. One of these is the live exploration. The live exploration is performed starting from a seed of URIs, and then recursively iterates on these URIs and finds at query time other links to other URIs that might contribute to the query result. Other approaches are the index-based approach. Obviously, since the approach is index-based, we construct an index to determine these relevant sources. So we have the sources, we build an index, and upon that index, we select the sources relevant for our query. The main two strategies are the multidimensional histogram and also the Q3. As regards the multidimensional histogram, we want to transform the triples RDF into points, 3D points, into the space. And so, if we have a triple like this, Bob lives in Berlin, we apply an hash function on this triple, and we obtain 3 points in the space that gives us the triple inside the histogram. Okay, so the histogram is all the space, and then for all the sources that are the triples that are inserted inside the space, we can divide our space into buckets. Buckets have a fixed dimension and collects all the triples inside these spaces. Okay. Obviously, the indexing is that each bucket contains an entry for all the data sources, but obviously we may have that the same data sources as multiple entries inside the index, since the data sources has multiple triples inside it. Okay. The Q3 is a combination of the histograms and the R trees, so we have a tree structure. The leaves are the buckets, so the spaces that contains the triples in hash points. And we have that obviously is more efficient for sources that are sparse, okay? So if we have some points like this, okay, these buckets are useless. So we think that we may use only this one, okay? And so the tree allows us to use only these spaces, and so we build the Q3. This structure is very useful for us, and we started from it to build the source selection caching framework. This is an overview of the framework we propose, and as you can see, we have the query. The query is given as input to the dynamic programming planner. The dynamic programming planner is a module inside our caching framework that looks for every connected subgraph inside the query and then generates the join plan. So it finds the best way to join the triples inside the query. As you can see, there is an integration with the cache controller. So we have a cache inside our framework. The cache contains some cached queries expressed with a label, and associated with this label there is a tree that we are going to see in a moment. Each entry of the cache has a link with the cached sources, so we have a list of sources that are cached, that are connected to the list of previous executed query that we have in our cache. The dynamic programming planner obviously can select for some triples, for some subgraphs of our query, one or more of these entries inside the cache, and so help the query processing, giving him some information that he already has about the sources. If there is an empty cache, so the query is executed using a standard approach, our source selection engine obviously uses some information given by the Q3, so we use this implementation for source selection, and then it gives you the final result, which is obviously the data retrieved for the query that the user has asked for. In this process, obviously, when we retrieve the sources for the query that I am giving it as input, I cache not only the query but also the sources that are associated with this query. And so I increment the cache, adding elements every time I retrieve information about the query. As you can see here, I told you that each entry inside the cache has a label and is associated with a tree. what is this label? This label is called canonical label, and is produced in this way. We have our query, and so for example, we want to know the name of a friend of two. I have a subject, and then we want to know the name of the friend of this subject, and then for this subject we want to know the name. Obviously the name of his friend is Mario. Okay? We have a dictionary for some values that are instantiated, so non-variables. And so for this predicate, we have an ID which is 23. We have an ID for this object which is 12. And then if we construct the graph associated with this query, and you can see that here there is a mistake, is question mark 2. We have that if we do this translation, we have the variable 1 here, then the translation of the predicate, which is 23, and then the variable 2. Then I use AND to express the join, and I have the variable 2, 23, because it's the translation of name, and then the translation, the ID of Mario, which is 12. Okay? So I have created a string starting from a query. This is useful since we can use this string as the label of each entry of our cache, but it is useful since we can create a tree associated with each entry. So you might think that for each entry inside the cache, we may have a label and then just one query. But we can create a tree which shares common part of the label. For example, this cache entry has this canonical label which is common to two queries, and the two queries builds the tree. These two leaves, L1 and L2, represent the information associated with these two queries. So for each path inside the tree, we have a different query. In this example, we have just two queries. For the first one, we have L1, which is the sources used for the evaluation of the first query, and L2 contains, obviously, the list of the set of sources used for the evaluation of the second query, with some other information, like the cost of those sources. With cost, we mean the total number of triples contained in all the sources associated with the query. But also we have a gain value, which is the contribution, the number of triples that contributes to the query result. So we save some information in here, and this information are propagated till the root. And here we have a cost value that allows us to choose the best cache entry when a query comes and it's matched with this cache entry. We have done on this evaluation some experiments. We have considered a data set of 1 million triples, more or less. Then we have considered 10 queries for each number of joins, starting from 0 join to 9 join. And we have considered only star queries, so queries done like this. We have a variable, like subject node, and then a number of joins, so a number of outgoing edges, that links to objects. Obviously, for 0 join, we mean that there is only one predicate connecting to an object. For 9 joins, we mean that there are 10 edges that connect the variable with the objects. Then we have generated the Q3 index, and it generates like 8,000 buckets. And these are some results. We have performed first a total match, so we have our cache filled with some values, with some entries. Then we run a query that matches exactly one entry of the cache. And as you can see, the red one are just using the indexing approach. The blue one is using our caching framework. we can see that obviously for zero join, so we have just one path, there is no caching, so the information, the cost, the time used by our approach is higher than just the index, since our approach is the index plus the caching, okay, and also plus the dynamic planner. So there is a cost that is given by this finding, the search of the subgraph connected inside our query. Then we can see that the time, the query time of the index is higher than our approach for each join. And then we have performed some evaluation also on partial matching. So there is some entries inside our cache, but our query doesn't match exactly an entry, but only a part of our query is cached. As you can see, here is not so clear. We have started from 4 joins till 7 joins, and we have done this experiment removing one triple pattern at time to the query. So we start from 4 triples inside the query, and then removed one, and see what happened if only three triple patterns on 4 matches an entry in the cache. And also here, we got some pretty good results. The last part of my talk today is on an approximation of this approach. So the exact matching is good. As you can see, the results are good, but does not allow to exploit till the end the cached information. So one reason is that queries are not always recurrent. One thing that is important for us that cache items are only the query that we define recurrent. So we have to find a way to understand when a query is recurrent. And also, for this reason, if I don't have a cache entry, I have to use a standard approach to retrieve the sources associated with the query. Relaxation allows us to consider also super query of our request, and this gives us fast answer, but obviously with lower accuracy. So we are considering a query which is not exactly the same, but it's something more general, okay? And the idea is to take advantage of RDF hierarchy, and so we look for predicates of the cached queries that are ancestors of the predicate of the query that are using now. And obviously we have to find a way to change the canonical label I presented you before. Here there is an example of an RDF property hierarchy. So we use an RDF hierarchy only on predicates. Predicates in RDF as a particular predicate, which is RDF as subproperty of, that links predicates one with another, and tell us that one predicate is a subproperty of another predicate. For example, we have here that champion is a parent of champion in single. Okay, we're talking about tennis, if I am not wrong. And obviously, champion in single female is a subproperty of champion in single. So we can use this hierarchy to rewrite our canonical representation of the labels. And here we have got an example. If we use a Dewey ID notation, which is mostly used in XML and other languages like that, to build a hierarchy using numbers, we can rewrite this hierarchy in this way. So we can create a generic prefix tree for our hierarchical notation. So if you can see here, we start from the root with 1, then the child is 1.1, the children of this node are 1.1 and 1.2, and so on. Okay? the generic notation is this one. So starting from the root, we have x1 till xm, okay? And so, for extending our canonical labeling algorithm, we have thought that if we have our RDF property hierarchy inside our caching framework, and so for example, we know that onPage is a subproperty of page, and so we can build the prefix tree like this. Okay? If we know that we want to create the canonical label of this query, we generate its graph, and so we know that 1 on page 2. Then, using this representation, we do not label on page like 2 using the ID 2, which is right for the starting canonical representation. If page has the ID 1, the second predicate we encounter is on page. So incrementally, it has like labels 2, ID 2. But using this hierarchy representation, we can say that the label associated with on page is 1.1. In this way, we can create a relation between queries that has predicates more general than the others. Okay? Just looking at the label. And for example, if we have this query, okay? If we use the canonical label, we have something like this, okay? Here I used the ID number 2, but the application can give it to a different value, okay? And so, looking at the cache here, we have no matches, okay? Since the exact matches here, there are no exact matches in the cache. But if we use the extended canonical label, and so 1.1, we have a match inside our cache, not exact match, because we have got 1 and here 1.2, okay? But we've got a relaxed match. In fact, on page we know that is a subproperty of page, so we can use this cache entry. Okay, so we can use the information associated with that cache entry. Obviously, is something which gives us a relaxed version of our query. So it gives us not the right sources for our query, but if we know that this query is a generalization of the one that we are using now, the results are good for us. Okay, also even if are not the same query. And so, to conclude, we have presented a smart caching approach for recurring queries on sources that are heterogeneous, diverse, and dynamic. We have presented a shortcut at the source selection step, and we have seen that the exact approach improves the source selection, obviously referring to the state-of-the-art indexing approaches. And we have seen that the relaxation allows us to extend further the caching approach, making them smarter in a way. What we want to do is define an algorithm to select this best cache entry. I've done a very simple example on relaxation, okay? But if we think that the cache may have n entries, we want to find the best one, okay? Best is like this. And also we want to evaluate both the exact and also the relaxed framework on different types of queries. We have tried already the exact framework only on star queries, but there exist a lot of kind of queries. And I finished. Thank you.
Thank you. Is there a question?
Just a curiosity. So function, so the return of the hash function is not used as spatial indexing, or maybe I got it wrong.
The hash function is used to create the index. So I've got for each source, I've got a number of triples that are contained in the source, and for each triple I generate the hash function, the hash value. So I got the subject, the predicate, and the object of one triple inside the source. And so I generate, using the hash function, these three coordinates, which represent a numerical value of the subject, of the predicate, and the object. Okay? This identifies one point inside a 3D space. Okay?
Okay, so but there is no, so the hash function is crafted to create some distance measure between points?
No, it creates points. If you give a string, the function returns you a value.
Okay.
And this value is used like a point inside the 3D space.
Okay. Because I was thinking to hilly trees,
no.
I have a font, so I just cut the space, but okay.
No, the space for multidimensional histograms is used to create buckets.
Okay.
But the buckets are fixed. So I have 9 buckets for, as the example before, but obviously in 2D. And so I have points inside all these buckets.
Okay.
The same thing is done in the Q3, but the Q3 stores only the buckets that has some points inside it.
Okay.
Okay?
Other questions? No, so thank you.
Thank you. Fai tu.